Hi everyone, and welcome back. This is going to be a lesson about row reduction and echelon forms. So we're going to basically be continuing the discussion from the previous video where we talked about row reduction and Gaussian elimination. We basically introduced linear systems and what it means to solve them. And we need to continue getting good at solving linear systems using matrices, things like that. Also in this section, I think we're going to see our first theorem of the semester. And another thing we need to get to today is, remember in the first video, we saw that there were three possible cases for a linear system. You either have one solution, no solutions, or infinitely many. Well, we haven't seen the infinitely many case in an example yet, so we're going to see that today. Anyway, let's go ahead and get started. All right, so like I said, we've got a few things to cover today. So this section is called row reduction and echelon forms. And I want to start by reminding you that earlier, the previous video, the previous lesson, we did row reduction where we had an augmented matrix representing a linear system. I'm not going to redo that whole problem, but this matrix should look a little familiar. Remember the right-hand side was 4, 10, 14. So that was one of the systems we looked at, the augmented matrix for it. And we did a bunch of steps, which all together, those steps are known as row reduction or Gaussian elimination. We did that to try to get the system into triangular form, because once it's in triangular form, we can use back substitution to find the solution. Well, this is what it looked like by the time we were done with the Gaussian elimination steps. And you might wonder, is it possible that maybe you could also get a different equivalent system? The answer is yes. You could actually do the row reduction steps a little differently. There's a little bit of flexibility there. So you could wind up with a matrix that looks a little different, but it still has the same solution set. But this is the one that we wound up at. We've got a little bit of terminology. The leftmost non-zero number in a row is called the leading entry of the row. When we talk about a matrix as a rectangular grid of numbers or a rectangular array of numbers, it has rows and columns. The matrix we're looking at here has 3 rows, 4 columns. It seems like we're talking a lot about the rows. We're not talking about columns so much. It seems like the rows are more important. And that's because each row represents one equation of a system. So 3 rows, 3 equations. And we are going to be interested in what is the leftmost non-zero number in a row. So, well, how about we look at this first one? In the first matrix, the leftmost non-zero number in the first row is 1. The leftmost non-zero number in the second row is 1. And the leftmost non-zero number in the third row is 3. So those would be the leading entries of these rows. But in the Gaussian elimination version of it, we have this 1 is a leading entry of the first row. This 1 is the leading entry of the second row. And this 1 is the leading entry of the third row. It's the leftmost non-zero number. Now, we're going to say that matrices that result from Gaussian elimination are said to be in row echelon form. Okay, so the title of this section said something about echelon forms, and you might be wondering, what is that all about? So that's what we're getting to here. Row echelon form, I wrote a little colon here. There's going to be two requirements to be in row echelon form. First of all, the leading entry of each row is to the right of the leading entry in the row above it. There's going to be one other requirement also that we're about to write. But let's think about this sentence. Is that true of this matrix here? Maybe if we look at like row 2, for example, and we look at the leading entry in row 2, is that leading entry to the right of the leading entry in the row above it? Yes, it is, because here's the one above it. It's kind of like we go down and to the right, down and to the right. And that's that triangular shape that we were talking about last time, or you could even think of it as a staircase. So we go down and to the right, down and to the right. That's what the sentence is saying. And then the other requirement might not really be so obvious because this hasn't really come up yet, but there is also a requirement that any rows consisting entirely of zeros are at the bottom of the matrix. All right, so we have not seen that happen in a problem yet, but at some point we will. If there is a row with all zeros, it has to be at the bottom. That's not a big deal. You know that we're allowed to interchange the positions of rows. Remember, that was one of the 3 steps that we're allowed to do. You can swap the positions of rows around. So if you had a row of all zeros, you could just swap it to be at the bottom. Not a big deal. All right, I want to show you a couple of quick examples, and not example problems per se. I just want to show you some quick examples of row echelon form, besides like the one that we have up above. All right, so I'm going to draw a larger matrix. I'm going to draw one with 4 columns and 4 rows. The numbers aren't super important here. I'm just trying to give us an example. I guess it's important which ones are zeros and which ones are not. By the way, when you have a matrix that has 4 rows and 4 columns, you might call it a 4x4 matrix. All right, so this is an example of, here, I have one more. I'll just draw both and we'll talk about them. All right, there we go. These are 2 examples of matrices that are in row echelon form. Let's look at this first one. So something maybe a little bit unexpected is happening. If you were thinking about looking for like this triangle shape, you might say like, well, here's a leading entry of 2, a leading entry of 1, but then like what happens in the 3rd row is a little weird because there's a 0 here. Maybe we were expecting something here that's not 0. But what I want to show you, how about this? I'm going to circle the leading entries in each row. So that's a leading entry of 2, leading entry of 1, The leftmost non-zero number in the third row is 3/2, and the fourth row doesn't have a leading entry because it's all zeros. And the important thing is that each leading entry is down and to the right, down and to the right. We could even kind of draw like this staircase pattern. It's just that the second step's a little longer than the first. All right, so this is in row echelon form. The second one, I could do the same thing here, I guess. Let's circle the leading entry here, the leading entry here, the leading entry here, and show you that we get this nice step pattern. It's lower left, it's all zeros. And of course, the one that we had up above to the right is also row echelon form. So lots of matrices can be row echelon form. As a little side note, I'm not going to write this, I'm just going to mention it. The word echelon, it means step. And it's because we get this sort of staircase structure that we use the word echelon. Now, we like matrices that are in row echelon form because we can quickly use back substitution to find solutions to a system. Or, by the way, another thing is we can quickly see if the system is inconsistent. Let me explain what I mean. Look at this second one here, this one here. If we think about what this would represent in terms of equations, there's 3 columns plus the fourth column represents sort of the constants on the right-hand side of the equal signs, right? Like, you know how I said that we could sometimes do this dashed line here? All right. So I think here this first row is basically saying x2 equals 0. All right, no problem with that. Second row is kind of saying negative 2x3 equals negative 2. All right, no problem with that. But this last row is saying 0x1 plus 0x2 plus 0x3 equals 3. So all together, that last row is saying 0 equals 3, which is nonsense. That's never true. So this is one of those cases, like we saw last time, where it's inconsistent. There are no solutions to this system. And that's one of the nice things about row echelon form is that we were able to see it pretty quickly. Now, the title of this section said echelon forms, plural. There was an S at the end of that. Echelon forms. And we saw this is row echelon form, but there's another one to talk about as well. So we can modify a row echelon form matrix to make it even simpler. I'm using the word simpler because I think that, when we do row reduction, we're kind of making an equivalent system, and in a way, it is kind of like simplifying. It's kind of like simplifying. We say a matrix is in reduced row echelon form. I'm going to underline that, reduced row echelon form. And we sometimes abbreviate this as RREF, reduced row echelon form. If we modified it to satisfy the following additional requirements. All right, so there were 2 requirements above. The two above are for being in row echelon form. there's two additional requirements for us to call it reduced. Okay? First one, all leading entries are 1. Okay, I think you could see that that is true for some row echelon form matrices, but it's not true for all of them. There's another requirement I have to tell you about. Real quick, before I tell you the other one, I just want to say, I circled the leading entries in some of these examples. These are not, they're not all 1s. So these are row echelon form, but they're not reduced. Okay. There is the additional requirement that every number above and below each leading entry is 0. All right, so we'll see some of these. We'll do this process of reducing one of these further to get it into this form. But you might look at it and say, like, is that even possible? Like, could I, if I took one of these that's in row echelon form, or even if we looked all the way back up here to this like original matrix that wasn't in any kind of row echelon form, if we were just given a matrix that represents a linear system, we did Gaussian elimination, we got row echelon form. You might wonder, is it always possible to do that? I don't think we've said for sure whether that's always possible to do that. And then furthermore, is it always possible to do this, to get it into reduced row echelon form? And this is going to be our first theorem of the semester. Which is appropriately titled Theorem 1. And it says, each matrix is row equivalent to one and only one reduced row echelon form matrix. So let me talk about this a little bit. We are saying in this theorem that every matrix can be turned into a reduced row echelon form. And not only that, but it can be done in only one way. What I mean by that is there's only one possible result. You could maybe do the Gaussian elimination steps in a different order. Two students might do different steps, but you're going to arrive at the same final reduced row echelon form matrix, which is pretty good because it's unique, and we like that. We like in math when something is unique. That's one of the reasons we like this reduced form. Another reason we like the reduced form is we're going to see that it helps us with solving systems even more than row echelon form did. The reduced form is going to help us even more for finding solutions. Now, the proof of this, we're actually not going to spend time in this lesson proving this. This is actually not even in the book section, but for the textbook that I'm referencing, it's in Appendix A. So I don't think that would be the best use of our time right now to prove that, although maybe it would be interesting to come back to it at some point and try to prove it. All right, I want to show you an example of getting a matrix all the way into this form. So what I'm going to do is let's say use row reduction steps to get the matrix into RREF, then solve the system. And I'm going to start us with one of the matrices we had above, which is one of the matrices from the previous video. All right. Now, if this is one of the matrices we had in the previous video, then you might say, hey, didn't we already solve this? Didn't we do back substitution and find the solution? Yeah, we did. We did. But I want to show you reduced row echelon form and what connection it has to the solution. So we already have row echelon form, okay? And we already have that all leading entries are 1. What would we do if they were not? Well, I guess if a leading entry here was not a 1, like if a leading entry here was a 2, we could always multiply that row by 1/2. So if we had a 2, we could multiply a row by 1/2. If we had a 4, we could multiply a row by 1/4. We could always do something like that to get all the leading entries to be 1. The remaining thing we need to do is every number above and below each leading entry needs to be 0. So actually, the problem now is like this -1 here, that needs to be a 0. And this 3 and this -2, they are above leading entries. They need to be zeros. So what I'm going to do, I'm looking for a way to start turning some of those things into zeros. And this is where you've got a little bit of flexibility. If you see a step that jumps out at you, give it a try. I am going to add 2 times row 3 to row 2. Do you see why I'm doing that? Not changing row 1 yet. Not changing row 3. I did that because I noticed that, all right, so 2 times 0 gets added to 0. 0. 2 times 0 gets added to 1. That's 1. 2 times 1 gets added to -2. That gives me a 0 here. That's the reason I was doing this step. I saw that this would get me a 0 here. And then finally, 2 times 3 is 6. That gets added to 1, so I get a 7. Now I think let's try to get rid of that -1, that -1 spot. Doesn't it look like we could do that by, add a multiple of a row to another row? So I'm going to add 1 times row 2 to row 1. So we get 1, 0, 3, 7 gets added to 4 to give me 11. And just copy the other rows. 0, 0, 1, 3. Does this fit the requirement of reduced row echelon form? So the first leading entry we see, everything below it, everything above and below it are zeros. The second leading entry, everything above it and below it are zeros. The third leading entry, it has a 0 above it, but it also has a 3 above it. This 3 is a problem. I'm going to put like a box around this. We need this 3 to be a 0 also, because that is also above a leading entry. So if I could get that 3 to be a 0, then we'd be in good shape. And I can do that. I don't think anything with row 2 is going to get that done. I think using a multiple of row 3 is going to get that done. So I'm going to add -3 times row 3 to row 1. So we get 1, 0, 0, and then we get a 2. All right, while you take a look at that, I'm going to get a sip of water. All right, so how are we doing? Did we get it into reduced row echelon form? Yes, I think we did. I'm going to put underneath this in parentheses. This is reduced row echelon form. All the leading entries are ones, and all the numbers above and below leading entries are zeros. And the theorem says that we can always do that. That's pretty cool because look at this. It's like really a much simpler matrix than what we started with. And I claim that from this, we immediately get the solution. So a cool trick here is, see the last column, 273? That's the solution, 273. And we got that solution last time by using back substitution and doing those steps. What we did right now was we did some extra row reduction instead, and we didn't actually have to do any back substitution steps. By the way, reading that last column out to get the solution, it's not just like it's some weird trick where the last column equals the solution. It makes sense if you think about what each row represents. The first row represents the equation 1x1 equals 2. The second row represents the equation 1x2 equals 7. So x2 equals 7. And then the last one is representing 1x3 equals 3. So x3 is 3. All right, so a little bit more terminology to tell you about this process we just did. So the process of converting a matrix to row echelon form, I'm not using the word reduced right now, is called, we know this because I know that I said this in the previous video, this was Gaussian elimination. I'm just restating it here to go with the things we're about to say. So when you convert a matrix to row echelon form using these kinds of steps, it's Gaussian elimination. All right, now for something new. The process of converting a matrix to reduced row echelon form. It's kind of like you do Gaussian elimination and then, plus a little bit extra. And it is called Gauss-Jordan elimination. It's the steps that we did above. The strategy or the process of doing it altogether is called Gauss-Jordan elimination. And a lot of textbooks, and the textbook that I'm referencing for this course refers to these methods as row reduction. So we might say, like, use row reduction to convert the following matrix into reduced row echelon form. Or we might say use Gauss-Jordan elimination. It's the same thing to us. What else can I say? So a little bit more on terminology. A pivot position. A pivot position in a matrix is a location of a leading one in its reduced row echelon form. It's basically where in the matrix do the leading ones appear when it's reduced. So if you're looking at a matrix that's already in reduced row echelon form, it's the ones. Like, we still have this on the screen, so I'll just point to it. We have, a pivot position here, another pivot position here, and a pivot position here in the third column, third row. So this has 3 pivot positions. But what we're saying is that even before you get it into that reduced row echelon form, you can still call those the pivot positions. They're the locations of where the ones are going to be once you get it into reduced form. They might not even be ones when you first start out, but they will be by the end of it. A related term is a pivot column. Is a column containing a pivot position. Okay, not a big deal. Pivot column is a column that has a pivot position. And, later on, these terms might be more important to us because we're going to start asking questions like, what's the significance of the number of pivot columns? Like, this problem up above, it had 3 variables, x1, x2, x3. Looks like we had 3 pivot columns. We had 3 pivot positions. Do you always wind up with the same number of pivots and variables? That's an interesting question, maybe. Can you have a matrix that has, fewer pivot columns? I'll just remind you real quickly that there was a row echelon form example here that had something where there were like all zeros in this column. Can something like that happen? What's going on with this one here? This third column here is a 0 there. So anyway, we'll talk more about that soon. So this stuff right here was just some extra terminology. What I want to talk about now is the textbook. The textbook describes row reduction as sort of a standardized algorithm that can be programmed into a computer. Do you know that computers are very good at working with like grids of numbers, an array of numbers? If you've ever done any programming, maybe you could imagine how you have arrays of numbers and rectangular grids of numbers are very easy for computers to work with. So the book sort of looks at row reduction from the perspective of a very standardized algorithm. It's like, do this, do this, do this, do this, and eventually you get to the result. I feel that in practice, there is flexibility in which steps you do. Just like in algebra, okay? Just like in algebra, there's a lot of flexibility. If you had like a equation you're trying to solve for x, 2 students might do it a different way, different algebra steps, but you might wind up at the same result. That's how I think of this. Right here, when we did this, I did this row reduction step to get a 0 here. And that was my choice, but some students might kind of do the other step first. We got a 0 in this position here. So which order do you want to do these 2 steps in? In my opinion, it's up to you. I don't think there's a wrong answer, do this step, or other way around. I think in the end, you're going to wind up doing about the same amount of work, and you're going to wind up at the same result. We know you're going to wind up at the same result because of the theorem. There's one and only one reduced matrix that you could get from this process. All right? So that's my little speech about flexibility in steps. So let's keep going. And what I'd like to do next is show you an example. So linear systems come in all shapes and sizes. Let's do one that's a little bit smaller right now. So let's say we're given 2x1 plus 4x2 equals 6, 3x1 plus 7x2 equals 12. I'm going to put the brackets to the left of it. So it's given as equations. And I'm going to ask you to try this. I'm going to ask you to write the augmented matrix and use Gauss-Jordan elimination to solve the system. Now, if we were in person, I would give you a few minutes to work on this. Maybe I'd walk around the room and see how it's going. Because this is a video, I'm just going to encourage you to maybe pause the video here, give this problem a try, and then you can hit play and, I'll walk us through the solution. All right, so let's talk about this. So when you found the augmented matrix, hopefully what you did was you made a little rectangle of numbers and you did 2, 4, 6, 3, 7, 12. That's the augmented matrix. And we'd like to get this into reduced row echelon form because it says Gauss-Jordan. So remember, a few minutes ago, I was talking about how there's some flexibility in which steps that you do. You want to get some zeros to show up in this matrix, right? But what I saw was I saw a 2, a 4, and a 6. Like this equation here, 2, 4, and 6. Everything is a multiple of 2. So I decided to do row 1 times 1/2. Because I thought if I do that, that might make things easier to work with. So that was my first step. If you did a different first step, that could still be okay. You might wind up doing something like that later, or you might not do it at all. All right, so now that I had that, I actually like that there's a 1 in the upper left there because ultimately we want that position to be a 1. At least I think we do. I'm going to try to get this 3 to be a 0. I can get that 3 to be a 0 because I'm going to add -3 times row 1 to row 2. So row 1 is not changing. Row 2 is getting stuff added to it. It gets a -3 added to the 3. It gets a -6 added to 7. And then -3 times 3 is -9 getting added to 12. This matrix we just arrived at right now, technically this is row echelon form. And we did Gaussian elimination, but we still have a little more to do. If we're supposed to use Gauss-Jordan elimination, we need to get this all the way into RREF, reduced form. So I'm going to go one more step. I think it's just that we need to get rid of that 2. We need that 2 position to be a 0 because that's above a leading entry. And I think the best way to get rid of that 2 is going to be to add a multiple of this 1. So I'm going to add -2 times row 2 to row 1. Row 2 is not changing, so I'm just going to copy row 2 real quick. Row 1 is changing. It gets a 0 gets added to the 1, so the 1 stays the same. -2 gets added to 2. And then -2 times 3 is -6. That gets added to the 3 that was here to become -3. This is now in reduced row echelon form. I'm going to write that underneath. We don't always have to label it, but I'm going to do it this time. And I'm going to say that from this, I can immediately see that the solution is -3, 3. This is the only reduced row echelon form that you should get. You might have some different steps in the middle of the problem, but the end of the problem should be the same for all of us. You do have to be careful with the arithmetic you're doing. Lots of little adding and subtracting mistakes can happen, so be careful about that. I'm sure I'll probably make some little mistakes like that as the course goes on. Happens to everyone, but one thing you could do is you could check your solution. You could take the solution and plug it into the original problem, and that might give you more confidence that you found the right solution. Let's see. Let's move on, and let's talk a little bit about a case with no solutions. I think we saw one of those in a previous video. Previously, we had one of these. I'm trying to remember if we solved it using a matrix or if we solved it just using equations. I think maybe we did use a matrix, but let's just have a quick recap of it. It was in a previous video that we saw this system. We try to do row reduction. We add 2 times row 1 to row 2 to try to make a 0 appear. And the problem is that we get something that looks like that. That row looks like it's kind of a red flag to me, okay? And the reason is because I know that the final column of this matrix, this augmented matrix, the final column represents the right-hand side. It's like the things to the right of the equal sign. So there's like something something equals 6. So I'm looking at this and thinking, this represents 0x1 plus 0x2 equals 6. Or in other words, 0 equals 6. And this is what we had last time, and I said this never happens. This is an inconsistent system. It has no solutions. So when you're doing row reduction and you wind up with a row like that, that's how you know there's no solutions. It's kind of telling us something nonsense like 0 equals 6. You might get something like 0 equals 1. You might get something like 1 equals 2. Just some kind of nonsense statement. It's usually going to be 0 equals something. Now, if you got 0 equals 0, that would be a different story. We'll talk about that in a minute. Because 0 equals 0 is true. Now, there is the one case we haven't seen yet in an example. And that is the case with infinitely many solutions. Do you remember in the previous video when we drew pictures of the 3 cases? I don't think I'm going to draw it again, but all right, basically, when you do a problem and there's one unique solution, that's kind of like it's kind of like there's 2 lines that are intersecting at a point. Okay, because there's 2 variables, so 2 equations, 2 variables. So it's like 2 lines, they intersect at this point in the xy plane. In the case with no solutions, it's kind of like we have 2 lines that never intersect. Another word for that is parallel. So this is really representing 2 parallel lines in the xy coordinate plane, even though it might not look like it at first. -4, 1, 1, 8, -2, 4, right? Do those look like they represent parallel lines? Well, it turns out that they do. If you were to convert this to like y equals mx plus b, try to graph them, these are 2 parallel lines. They never touch. The case with infinitely many solutions is supposed to be the case where you have 2 lines that overlap each other. So let's look at an example of this. Let's say that we want to solve 3x1 minus x2 equals 6 minus 6x1 plus 2x2 equals negative 12. And I'll do this one for us. I've already kind of spoiled the answer. But there are some questions that you should have here. You should be wondering, first of all, how are we going to find that it has infinitely many solutions? Second of all, how are we going to write the answer? Are we just going to say infinitely many and put a box around it? There's actually something else that we're going to do. All right, let's get started. Let's just try, let's pretend we don't know the answer, and let's just try row reduction. Augmented matrix, this is supposed to be our standard method for solving systems, so let's do this and see what happens. That's my setup. Start like that, and I figure out what am I going to do next. I think getting rid of that negative 6 looks pretty easy because there's a 3 above it. So like if I did 2 times 3 and add that to the negative 6, that would work nice. I'm always looking for something like that. Like what multiple of row 1 would I have to add to get rid of this negative 6? So I am going to add 2 times row 1 to row 2. I'm doing that to get rid of the negative 6. You get a 0 there. But as you know, as sort of a consequence, a side effect of doing that, we also have to do that to all the other entries in that row. I mean, the negative 6 is the one that I was sort of targeting, but we need to change the 2 and the negative 12 appropriately. So let's say, all right, 2 times negative 1 gets added to 2. That's also going to give me a 0. And 2 times 6 gets added to negative 12. That's also going to give me a 0. Okay, so this is the first time we've had this happen. A row entirely of zeros. Now, what does this mean? This represents, like in terms of an equation, this is kind of saying 0x1 plus 0x2 equals 0. Right, because those are like the coefficients. And this simplifies to just 0 equals 0. By the way, this row or equation is supposed to tell us what x2 is, right? Because generally the first row tells us what x1 is. The second row tells us what x2 is. It's not really telling me what x2 is. Let's get a fresh sheet of paper here. We need to talk about this. All right, first of all, I'll just say in parentheses, this is always true. What I mean by that is it's true no matter what I put in for x2. 0 will always equal 0. So this means, because this came from row 2, this means x2 can be any number. So I'm saying that row 1 typically tells us what x1 is. Row 2 typically tells us what x2 is. And because we got this, it's telling us x2 can be anything. We say x2 is a free variable. I'm going to underline that. And we say x1 is a basic variable. So a free variable is a variable that can be any number, any real number. A basic variable is any variable that isn't free. When I say any number, I mean any real number, just so you know. All right, let's look at row 1. Row 1 In the sort of row reduction step, we got 3, -1, 6. There's a 3, -1, 6, and it means 3x1 minus x2 equals 6. And I'm going to say we'll solve for x1 in terms of x2. Solve for x1 in terms of x2. It feels like that's normally what we would do, except normally we would have like a specific thing to substitute in for x2. And right now we don't have anything specific to substitute in for x2, so we're just going to leave it as x2. But we're still going to solve for x1. So 3x1 equals x2 plus 6, which means x1 equals 1/3 x2 plus 2. What we're doing is we are finding a way to describe the solution set. And I'm going to show you 2 different ways that we can write it. Solutions, plural, because this does have more than one solution. We could write it as an ordered pair, something comma something. Usually we write x1 comma x2. I'm going to write what we found for x1 comma x2 is just x2. Or another way to write this is you could say x1 equals 1/3 x2 plus 2. x2 is free. Those are 2 ways to write this solution set. Let me remind you that in the previous video, like what's going on here graphically, like if we were to try to graph this stuff in the xy plane or the x1 x2 plane, we have 2 lines that overlap each other. They're really the same line, and I think that you could look at this system and you could figure out that you could rearrange those 2 equations to actually be the same equation twice. When 2 lines overlap each other, we want every point on the line to be one of the solutions. Every point on the line is a solution. So there's infinitely many solutions. That doesn't necessarily mean that every point in the xy plane solves this system. Let me be clear about this. If you just picked like a random x1 and a random x2, it probably would not solve this system. You know, if I try 5 comma 7, or if I try, 10 comma 100, chances are if I pick random numbers, it's probably not going to work. So not everything is a solution to this, but everything in this form is a solution to this. So pick any real number for x2 and pick the appropriate x1, and that will solve the system. For example, let's say x2 can be any real number, so let's say x2 is 0. That's one possibility. Then you could have, put 0 in here, so you'd have the point 2 comma 0. That is one of the solutions to this system. This is really describing like a family of solutions. They all fit this form. You could put in x2 is, let's say, 3. And then when you do this, you'll get 3 comma 3. So that should also be a solution. In general, we write basic variables in terms of free variables. All right, so we just say x2 is anything, and x1 is something in terms of x2. This is called a parametric representation of the solution set. I'll just put in parentheses, x2 is sometimes called a parameter because we're writing x1 in terms of x2. Now, there are also other ways to write this solution set that we might see in some upcoming sections, but for now, these are two good ways to write it. I want to show you another example. Okay, let's get another example here. And I'll do this next one also. You'll have some other ones to practice. All right, example. Let's talk about solving x1 minus 3x2 minus 5x3 equals 0. x2 minus x3 equals -1. And I'm gonna do Gauss-Jordan elimination, even though I didn't say it. We're gonna try to do that, see what happens. Now, this problem looks different from other ones because there are 3 variables, but this time there are only 2 equations. It seems like most of the problems I've been showing us, it's usually been either like 2 equations, 2 variables, or 3 equations, 3 variables. Now we have kind of a mismatch. That's okay. We're going to work on it and see what happens. We'll still try to do the augmented matrix. So I guess 1, -3, -5, 0. What goes here? 0. So 0 x1's here. 1, -1, -1. Okay. This is what we start with. I would actually say that this is already in row echelon form. Already in row echelon form. Because if you went back to earlier in this video, when we had the definition of row echelon form, there were only 2 requirements. The leading entry in each row is to the right of the leading entry in the row above it. So yeah, we do have that kind of staircase pattern happening here in regard to leading entries. The other requirement was that any rows consisting entirely of zeros is at the bottom. We don't have that. So this is row echelon form. It's not in reduced form. So I would like to go do like maybe 1 row reduction step to get this into reduced form. And I think that means trying to get rid of this -3. If we could turn that -3 into a 0, I'd be happier with this. So I'm going to add 3 times row 2 to row 1. Because reduced row echelon form is going to be about as simple as we can make this, and then we'll talk about the solutions. Let's see. -3 gets added to -5 to get -8. And -3 gets added to 0 to get -3. Okay. Now, can we go any further? Do we need to go any further? I claim that this is reduced row echelon form. It already fit the criteria of row echelon form, but now it's reduced because every leading entry is 1, and everything above or below a leading entry is 0. So it does fit that definition. I want to show you something. Remember we were talking about pivot positions and pivot columns? So sometimes we circle the pivots. So I'm going to circle like this 1 and this 1. And I'm going to just indicate underneath. These are the pivot columns. Okay? This problem just looks different from other ones because we have this extra column here with these extra numbers just sitting there. We need to talk about, like, well, what does that mean? What we are going to conclude from this is that columns 1 and 2 have pivots. So it turns out that what we can conclude from this, remember, like, what does each column represent? The first column is kind of the x1 column. Second column is like the x2s. Third column is the x3s. Fourth column is the right-hand side. So the x1 column and the x2 column have pivots. This means that x1 and x2 are basic. Column 3 has no pivot. So column 3 corresponds to the x3 column. There's no pivot there. Well, if I said that those other ones were basic, you're probably going to guess that this means x3 is free. So we'll write, what do? We write basic variables in terms of free variables. So we will write x1 and x2 in terms of x3. I know that there's infinitely many solutions. As soon as we figure out that there is a free variable, as soon as you know that there's at least one free variable, it means there's infinitely many solutions, and you have to come up with some way of writing the solution set, which we are calling a parameterization of the solution set, or a parametric representation. Let's see. Let's see what row 1 is telling us. Row 1 looks like this. Right? I'm just copying row 1 right now. And this means, it means x1 minus 8x3 equals negative 3. Right? Hope everyone can see that there's 1x1 plus 0x2 minus 8x3 equals negative 3. I would like to write x1 in terms of x3. So I'm going to rearrange this to be x1 equals negative 3 plus 8x3. So I just wrote x1 in terms of the free variable. Okay. And then we'll do the same thing from row 2. Row 2 tells me, let's see, let's write it first. Row 2 of the reduced form. This means, or this represents, x2 minus x3 equals negative 1. 0x1 plus 1x2 minus 1x3 equals negative 1. I'm going to rearrange this to get x2 in terms of x3. So x2 equals negative 1 plus x3. I'm ready to write the answer. The solution set, technically the parametric representation of the solution set. There were 3 unknowns, so we should say something for all 3. x1, x2, and x3, right? I'm going to say x1 is what we found for x1. x2 is what we found for x2. x3 is free. That means that x3 can be any real number. And anything you come up with that fits this description for x1, x2, x3. So like pick any real number for x3. Pick your favorite real number. Put it into x3. Find the corresponding x1 and x2. And it will be a solution to this system. Or, if you prefer, you can write it as... You write it like this. Sometimes we call them coordinates. This is kind of like representing points in three-dimensional space. There's my x1. There's my x2. What do we write for x3? Well, x3 can be anything. We just write x3. So any point that fits this format is a solution to this system. All right, I'll give you just another moment to copy any of that down before we wrap things up. All right, so that is the end of the section for us. We kind of packed in a lot there, didn't we? So, first video lesson was an intro to linear systems and Gaussian elimination. This video took it further, right? We talked about echelon forms, two of them. There's row echelon form, and then there's the reduced row echelon form. And I think at this point, what I'd really like is for you to be comfortable solving systems, solving the types of problems we did of these size problems. Maybe 3 equations, 3 variables. You should be ready for some systems that have one unique solution. Or you might get some problems that have no solutions. You should be able to identify that. You might get some problems that have infinitely many solutions, and then we kind of answer them like those last two that we did. Those can be a little tricky. We'll see more of those in upcoming sections, I think. So what's coming next for us in the next video is we're going to talk a little more about matrices as just objects in general, and like other things we can do with matrices. Besides just solving systems, they're also just kind of interesting objects on their own. Yeah, so make sure you are doing some practice problems, not just watching these videos, but also doing some practice problems of your own. And, we want to make sure that you're comfortable with solving systems. I think sometimes people say in linear algebra, I've heard it said in that every math problem in linear algebra can be reduced to just solving some kind of system. Maybe that's an exaggeration, but the idea is that later in the course, when we do some more advanced things, there'll be some more complicated problem, but we're going to turn it into just, can you solve this specific system associated with this problem? So you need to be good at solving systems. All right, that's enough from me for today. So I'll see you in the next video when we talk about vector equations. Have a good one.